So this is my screen recording for project turn-in number 2. First problem is a heat transfer analysis on meatballs. And you're assuming meatballs are spherical, constant thermal properties. And for part A, assume a BO number of less than 0.1. So we can apply lumped analysis. These properties of ground beef were found and given. And so first, you're going to solve for LC and the B value with units of 1 over time. And you're finding the temperature after 20 minutes of in the oven. So you plug in the equation for lumped analysis, solve for T at 1200 seconds, and you get 105.5 degrees Celsius, which seems a little high, so we're going to assume 1D heat transfer. Solve for a BO number, which is in fact larger than 0.1, which means lumped analysis could not have been used. And we can interpolate table 4-2 to find lambda in A values. We then need to find tau to plug into the simplified theta equation to solve for the temperature at the center of the sphere. And we have everything but T of T at 1200 seconds, and we find that temperature to be 93.5 degrees Celsius, which seems to be more accurate. Overall, this almost 12-degree temperature change is mostly dependent because lumped analysis was incorrectly applied to this scenario. But another minor error could have been that the temperature of the meatball was probably a little higher than 0 degrees Celsius initially. But again, mostly because of the false application or incorrect application of lumped analysis. And then for part B of this question, I wanted to drive the spherical coordinate system for the meatball. And you're assuming the meatball is not generating any energy. I have the area and volume equations for a sphere there, and then start with the basic energy balance of sum of energy in minus sum of energy out is equal to the change in energy over time. You then can apply that big Q is equal to lower Q times area, plug in areas, and then take the limit that the change in the radius and the change in time approach 0, apply Fourier's law, plug in alpha, and you get 1 over r squared is equal to d times r squared. dt dr over dr is equal to 1 over alpha, change in temperature over change in time. With the two boundary conditions that the center of the meatball at r equals 0, change in temperature per the change in radius is equal to 0, and then on the outside, conduction and convection heats are equal. For the second problem, we have a glass door with an area of 2 meters squared, and we're applying steady heat transfer, one-dimensional heat transfer, as well as constant conductivity and no radiation of the glass door. We want to find the inside temperature of the glass, T1. And first we can draw the resistance map here and solve for all 3 resistances, the 2 convective resistances on the inside and outside of the glass, as well as the conductive resistance of the glass itself. Find the total resistance, solve for heat, or the total heat transfer Q to be 363 watts. We then apply analysis on the left side of the resistance map, where the only resistance is convection 1, to solve for temperature 1 to be 11.8 degrees Celsius. For the next problem, I wanted to drive the Cartesian coordinates for the above system, which is no energy generated by the glass and a 1D steady state heat transfer. So this equation will be simplified down quite heavily. Again, start with the basic energy balance of energy in minus energy out is equal to change in energy over time. The 3-dimensional one is given there, but since this is a 1-dimensional, you can cross out the y variables, x variables, and energy generation. We can then apply Fourier's law to plug in for the little q's, and then also steady state to make the right side of the equation equal to 0. Temperature is not changing with time at steady state. Then we could do a little calculus, take the derivative, divide over k, and we get the double derivative of temperature per x is equal to 0. With boundary conditions of a steady surface temperature and convection, conduction, symmetry, just like the spherical coordinates. My fourth problem is mass transfer on a rubber ball filled with nitrogen gas, which Guinness Beer Company is actually using. They're putting these balls into their cans to release nitrogen gas when the can's open to make it smoother and better tasting. But I wanted to see how much of the nitrogen gas gets through that rubber ball when the beer is just sitting at room temperature unopened. And so you can assume steady mass diffusion, one-dimensional diffusion, no chemical reactions, and a low concentration of nitrogen gas inside the ball. Using table 4-13 and handout 1, you can find the diffusion constant of 1.5 e to the negative 10 meters squared per second. We can then apply the molar diffusion rate of 4 pi r1 r2 times that constant over the concentration, change in concentration over the change in radius. We're given the diameter and the thickness of the ball, so we can solve for R2 and R1, plug it in, find for the molar diffusion rate, and then multiply the molar diffusion rate by the molar mass, which is 28 kilograms per kilomole for nitrogen gas, since there's 2 of them. 14 times 2 is 28, and the mass flow rate is then going to be 1.77 e to the negative 10 kilograms per second.